Hello everyone, our work focuses on the task of cross-view localization. The problem is straightforward. Imagine we have a ground-level photo, along with its coarse GPS tag, which can be off by tens or even hundreds of meters. Our goal is to use this coarse location to define a search area on a satellite map, and then pinpoint the exact position of the ground photo within this area. This allows us to retrieve the precise GPS coordinates. To address key challenges in this task, such as poor generalization and the scarcity of labeled data, we propose GeoDistill, a novel geometry-guided, weakly supervised self-distillation paradigm. Our approach is inspired by how humans intuitively solve this problem. We don't match pixels. Instead, we look for geometrically consistent structures, like the footprint of a building or the layout of a road. As you can see, even though the visual appearance is completely different, a building's facade versus its roof, these underlying geometric cues are invariant to the viewpoint change. This is the core insight behind GeoDistill. We aim to train a model that learns to focus on these stable shared geometric features rather than on transient view-dependent textures. By doing so, our model can achieve not only high accuracy but also strong generalization to new areas, as these geometric structures are universally present. There is a critical challenge in cross-view localization: the scarcity of precise training labels. Acquiring accurate GPS labels for ground-level images is prohibitively expensive. Unlike typical annotation tasks like object detection, correcting GPS data requires specialized equipment and a trained person to mitigate inherent inaccuracies found even in commercial systems. Unfortunately, most existing cross-view localization methods are fully supervised, relying on precise GPS label for training. This dependency on strong labels, combined with the generalization issues we mentioned earlier, severely hinders their large-scale real-world development. To overcome this bottleneck, GeoDistill adopts a weakly supervised paradigm. Our approach dispenses with the need for precise GPS labels and instead learns from widely available yet noise-coarse GPS prior. So, in weakly supervised setting, a crucial question arises: where do we get our supervision signal from? Our key idea stems from a simple geometric prior we called field of view consistency. Think about it. If you stand at one spot and take multiple photos, whether it is a full panorama or a narrow snapshot, all these images share the exact same geographically coordinate. Therefore, they must be localized to the same point on the satellite map. This insight inspired us. We can simulate different FOVs by applying FOV-based masking to a ground image, generating multiple views of the same location but with varying content. This could teach a model to focus on view-invariant features. A naive approach would be to use this masking simply as a data augmentation technique during training. However, our experiments revealed this to be counterproductive. Instead of helping, it made the already challenging task even harder by reducing the available information, leading to a slight performance drop. So, while simple augmentation fails, we realize there is a far more elegant way to leverage this powerful FOV prior. To elegantly leverage this FOV prior, we designed GeoDistill, a teacher-student Self-Distillation framework. Our core idea here is in a fundamental shift in the objective. Instead of forcing the model to predict a precise label from the incomplete data, which is extremely difficult, we enforce a much more reliable goal: prediction consistency across different FOV. In practice, we feed the full unmasked image to a teacher model, while a student model sees only a randomly masked version. Both models start from the same pre-trained weights, but this difference in input creates a knowledge gap. The student's job is to distill the teacher's high-quality reasoning, forcing it to learn the most stable and generalizable geometric cues. Now, directly predicting all three degrees of freedom, x, y, and rotation, is still very complex. So, to further simplify the problem, we decouple it into two manageable stages. We first predict and correct the rotation, and only then, with the view aligned, do we apply our teacher-student distillation to robustly predict the final 2D translation. This divided and conquered stage makes the entire process more robust. Here is the quantitative results of GeoDistill. What is the key takeaway from these numbers? It is that GeoDistill allows models to better learn the underlying data distribution. We achieved these significant gains without changing model's architecture and without using any extra data. It is a pure enhancement of the training process itself. By simply enforcing geometry consistency during training, we enable the model to extract more robust patterns from the existing data. For example, on the changing cross-area task for vigor, we see up to a 25% error reduction. This demonstrates that our method effectively forces the model to learn more generalizable geometric features from the same amount of data, unlocking its true potential. Our qualitative results clearly show the impact of GeoDistill. Here's a typical failure case for the base model on the left. The heat map is weak and the confidence at the true location is near zero. On the right, you see the result with GeoDistill. Our method transforms this failure into a confident and accurate prediction. The heat map becomes sharp and correctly localized. This is a direct result of our self-distillation paradigm. It effectively teaches the model to be robust to viewpoint changes and to rely on stable geometric cues. In essence, our method fixes these failure modes by making the model's decision-making process more robust.